Everyone, welcome back to a new video on our channel. So today we'll be covering a new topic, sequences and series. This is part 1 of our 2-part introduction to this topic, and we'll be covering the topics of arithmetic progression and geometric progression. So this one over here. In our next video, we'll be covering summation of unknown sequences using both method of difference and by manipulating given formulas. Alright, so starting off with the arithmetic and geometric progression. So what is an arithmetic progression? Sounds kind of chim, right? So sometimes we call it AP, but an arithmetic progression is basically a sequence with a fixed common difference. So for example, you see 1, 3, 5, 7, 9, 11. The common difference here is 2, right? So plus 2, plus 2, plus 2. So the difference between two terms next to each other is the same. So this is an AP. And as for 20, we minus 8, we get 12, minus 8, we get 4. So these are both APs. Okay, so in general, a sequence of AP will look like this. So U here means which term lah. So U1 means the first term. We denote the first term using the letter A always, even in the other one we're going to learn later, geometric progression. And here our common difference, the fixed common difference, is D. So the second term, U2, will be D more than the first term. So if the first term is A, then this is A plus D. And the third term will be A plus D plus another D, so A plus 2D, so on and so forth. Until we get the general formula for the nth term as A plus n minus 1 times D. Alright, so moving on. So there's actually a shortcut to find the sum of arithmetic progressions. So an easy way to think about this is, say you're given an arithmetic progression 1, 3, 5, 7, 9, 11. Now, what we can do is we can pair the numbers up, right? So we take the first number and the last number, we get a sum of 12. And we realize all the interior pairs also add up to 12. And the number of pairs is just the total number of elements, which is the total number of terms in this AP, divided by 2. So since there are 6 terms, there will be 6 divided by 2 pairs. And each pair adds up to 12, which is the first term and the last term. So this is the sum of our AP. So if you look at it in this formula over here, n is the number of terms, divided by 2 because n over 2 is the number of pairs we have, right? And then now we want to find the sum of each pair. So we look at the first term being A, and the last term being A plus n minus 1 times D, right? So we just add it like this. So if we combine these, we realize we actually get this. So an easy way to remember it is just take the first term plus the last term. This will give you the sum of each pair. Then multiply it by the number of terms and divide by 2. So this will give you the number of pairs. Sum of each pair. Okay, so what happens if there's an odd number of numbers? Then there's one number that's going to be unpaired, right? But you can actually use the same formula. So the way to think about it is a bit different. So let's say you have 1, 3, 5, 7, 9, don't have 11. Okay, so we duplicate this AP and write it backwards. So now the sum of all these numbers is twice of the original sum that we wanted, right? And now if we add up all the numbers vertically, we will get 5 pairs, which is n, right? In general, the number of elements. N pairs of 10, 10, 10, 10, 10, 10. And the sum of each pair is this thing in this big bracket over here. And then we divide by 2 because we duplicated it just now and we only want the sum of one of those APs. So it's actually the same thing lah. Alright, so next we come across questions which ask us the question slightly differently. So instead of asking us to find the sum up to how many terms or whatnot, this question gives you it in the opposite manner. So they tell you the general formula for the sum. Sn here is the sum of the first n terms, u1, u2, all the way to un of this arithmetic progression. Okay, if Sn equals to n squared, which means they give you the general formula for the sum already, then they want you to verify if it is an arithmetic progression. So as we can see, this is actually kind of like the opposite, right, of what we were doing just now. So we are given a sum and we want to show it's an AP instead of being told that it's an AP already. So what we can do is we can try writing out some small values first. So S1 will be equals to 1 squared equals to 1. And since the sum of the first term is equals to the first term itself, this will mean that U1 equals 1, right? Okay, now S2 equals to 2 squared equals 4. So the sum of the first two terms is equals to 4. Since the first term is 1 already, the second term should be 3. If we write S3 equals 3 squared equals to 9, then we get U3 equals to, the sum of the first three terms add up to 9. Since the first two terms already add up to 4, so the next term should add up, the next term should be 5. So it looks like an AP, right? 1, 3, 5, 7. Okay, so we want to show if this is an AP. So we start with observing that we can take two separate sums, Sn minus 1 and Sn. And what happens when we take the sum of the first n minus 1 numbers? We will get u1 plus u2 all the way to un minus 1, right? And if we look at Sn, we'll get the sum of the first n terms. So we'll get what we had previously plus an extra un, the one written in red over here. So a way to actually calculate un could be to take Sn, this entire big chunk over here, and subtract it with what we had above. So if we take Sn minus 1, we should expect to get un. Alright, but in this case, so un equals to Sn minus 1. But of course, this only works for n greater than or equals to 2, because n minus 1 has to be at least 1, because you can't have the sum of the first 0 terms. So how we start our working is we write for n greater than or equals to 2, un equals to Sn minus Sn minus 1 equals to, Sn is just n squared, right? So n squared minus Sn minus 1 is n minus 1 squared. Okay, so if we expand this out, we get n squared minus 2n plus 1, which will just give us 2n minus 1. Okay, so we got the formula for un, the general formula for un for n greater than or equals to 2. But we still have to check n equals to 1 as well, right? So we have to verify that u1 satisfies this relation as well. So u1, this is very important as you'll see later, okay? u1 equals to 1, right? Because s1 equals to 1 squared. And since 1 does satisfy 2n minus 1, because 1 is equals to 2 times 1 minus 1, so we say it follows the form un equals to 2n minus 1 when n equals 1. And thus, we can conclude that for n greater than or equals to 1, we can write un equals to 2n minus 1. Okay, for n greater than or equals to 1. Previously, we were only able to verify it for 2, right? Because n minus 1 here, the subscript of this sum had to be at least 1. So now that we have this identity, un equals to 2n minus 1, now we proceed to want to show that for an arithmetic progression, the common difference has to be constant, right? And the common difference here, okay, common difference is equals to the difference between any two adjacent numbers. So numbers next to each other. So maybe un minus 1. So let's try and figure out what un minus 1 is. Okay, so this is the presentation. So you write un minus 1 equals to, okay, so recalling un is equals to 2n minus 1, right? So we write 2n minus 1 minus bracket 2n minus 1 minus 1. And if we calculate this, this is actually equals to 2, which is a constant. Okay, so you conclude by saying, since the difference between every two consecutive terms is a constant, hence the sequence is an AP. Okay, so this is roughly how we show a sequence is an arithmetic progression. So remember, we first check n greater than or equals to 2. Then we have to make sure that n equals to 1 works as well. Okay, so let me give you an example of why n equals 1 fails to, it's very important to check n equals 1 sometimes. Alright, so let's look at this sequence over here. Sn is equals to 2n squared plus 5n plus 2. And they want you to check if this sequence is an arithmetic progression. Okay, so how do we start by doing this? We do the same thing. We write for n greater than or equals to 2, un equals to, say, Sn minus Sn minus 1, which is equals to 2n squared plus 5n plus 2 minus 2n minus 1 squared minus 5n minus 1 minus 2. And this will be equals to, let's see, 2n squared plus 5n plus 2 minus 2n squared plus 4n minus 2 minus 5n plus 5 minus 2. And this would give us simply 4n minus 2. Okay, so at first glance it might look like un minus 1 is bound to give us a constant, right? So it will look like 4n minus 2 minus 4 times n minus 1 plus 2, and this would just give us 4. So the common difference should be 4 here. But if we were to check u1, right? Okay, let's see u1. u1 is equals to s1. So u1 equals to 2 times 1, which is 2, plus 5 times 1, which is 5, plus 2, which is equals to 9. And we realize that it doesn't actually satisfy 4n minus 2 over here, right? Okay, so that's a brief overview of why, okay, sorry, it's not minus 2 here, minus 2. It's actually equals to plus 3. I wrote wrongly, sorry. Okay, but we'll actually come to realize that it doesn't actually satisfy this relation over here. And what does this mean? It means that u2, u3, u4, u5 all form an arithmetic progression, but the first term doesn't form an arithmetic progression. So this is very tricky, and it's always important to check your u1 first, okay? So now I'll be moving on to the next kind of question. So the next kind of question we can have is on geometric progressions. So a geometric progression, we usually call it GP, is very similar to an AP. So we kind of have something like a common difference, but in this case, it's a common ratio. So instead of adding to the first term, we multiply from the previous term. So 1, 2, 4, 8, 16 is a GP because we times 2, times 2, times 2. And as for this one, the common ratio would be multiplying by negative 1/3, then multiplying by negative 1/3, and so on. So the common ratio doesn't have to be a nice number, it can be some negative fraction or whatnot, okay? So in general, a sequence of GPs can be represented as follows. Our first term is still A, our common ratio is R, so we have AR squared, so on and so forth, until the nth term is A times the common ratio R to the power of n minus 1. Okay, so let's try and find the sum of the geometric progression. Okay, we're going to do this in a systematic way. So the sum of the first n terms. These are the first n terms, right, of the geometric progression. So let's try and find this sum. So what we can do is we can write it out in this form, as in a previous table. So we have AR squared, and so on and so forth. Okay, so what happens when we multiply everything by R? So the left side becomes R times S to the power Sn, and every single term on the right will be multiplied by R. So A becomes AR becomes AR squared, AR to the power of n minus 1 becomes AR to the power of n. Okay, so now you realize that there are actually a lot of overlapping terms between these two. So what can we do? We can take the larger one and subtract it with this smaller one. So we get R Sn minus, okay, sorry, this is just moving ARN over to the left first. rsn minus ar to the power of n equals to ar plus all the way here. So we're just moving this over first. And next, right, remember we compared these two, and this part here makes up this part. See, the thing in the blue box over here is the exact same as what's written in my curly brace over here. So what we can do is we can actually take this one and subtract a from both sides to get Sn minus a, and then the two blocks will be the same. So we can equate them together. And this is a very neat trick because all the terms will eventually cancel out and only leave us with a few terms. Okay, so if we rearrange this, we will get, sorry, let me move this away. We will get Sn equals to this formula over here. So this is a formula that you must know, but the derivation might not be 100% necessary, but it's very good to know because sometimes they can lead you to derive this in the exam paper. So this is the formula you have to remember for the sum of the first n terms of the geometric progression. Okay, so geometric progressions can go all the way to infinity. Okay, so what this means is, if we consider an infinite geometric progression with an infinite sum, then we have to, sometimes in the exam they call it convergent. So it means that the sum gets closer and closer and closer to a certain value as you increase the number of elements. So you increase your n basically until you add it all the way to infinity. It should, they call it converge. Okay, the sum should converge. So the sum to infinity is equals to this formula over here. It's very, very, very elementary and simple to memorize. So it's equals to a over 1 minus r. So if we look at the original formula for the sum of the first n terms, we realize that as we increase n further and further towards infinity, right? Okay, first we have to look at the necessary conditions. The necessary conditions for this sum to exist. This is the most important thing. Okay, so your common ratio has to be between -1 and 1. If the common ratio is not between -1 and 1, let's say our thing is 2, 4, 8, 16, 32. This sum will go on and on and on forever to infinity, and we won't be able to find the sum to infinity because it won't be converging at a nice number. Okay, so we have to have some kind of sequence like maybe 1, half, 1/4, 1/8. Here your common ratio is half. Okay, so we want to find the sum of this all the way to infinity. Okay, so now that we know that this is the necessary range between -1 and 1, what we realize is that as n approaches infinity, right, this thing to the power of n will get closer and closer and closer to 0. So your thing on top here will eventually just become 1. So your sum to infinity is just a over 1 minus r. Again, this is a very important formula. So if we apply it to this question right here, our sum to infinity is just a, 1, over 1 minus the common ratio, which is half. And this is equals to 2. So 1 plus half plus 1/4 plus 1/8, so on, so on, so on, all the way into infinity will be equals to 2, which is a very beautiful thing. Okay, so what happens if r equals to 1? Okay, well, if r equals to 1, then it doesn't really make much sense for us to be finding the sum of the geometric progression, right? Because all the terms will just be the same. It just be, let's say 2, then the next number is 2, 2, 2, 2, 2. So this is a bit pointless, and if we look at the denominator over here, you can't put in r equals to 1, if not it will be equals to 0. So the sum to infinity when r equals to 1 is undefined. So it has to be in between, strictly in between -1 and 1. Okay, so lastly, we are going to show that a sequence is a GP. So how do we do this? So in order to show that a sequence is a GP, we actually just do the exact same thing as we did for an AP, but instead, we still, everything in front is the same. We still want to do, for n greater than or equals to 2, un equals to Sn minus Sn minus 1. Then we want to show that u1 is equals to this formula over here as well. But now instead, we want to show that instead of un minus 1 being a constant, we want to show that un divided by un minus 1 is a constant. Okay, because this is our common ratio. So we want to show that this is a constant. And if we are able to show that this is a constant, you just need to say since the ratio of every two consecutive terms is a constant. Therefore, the terms of this sequence form a geometric progression. Okay, so now we're going to combine the AP and the GP, and we're going to look at this first type of question first. Okay, we're going to look at problems involving the manipulation of algebra using various concepts in AP, GP. And as for real-life word problems, you're going to be covering it in another video to come. Okay, so let's look at algebraic manipulation. So questions will have preambles looking like these. So they might say arithmetic series and geometric series have blah blah blah. They tell you the first term of the arithmetic progression, first term of geometric. And then they like to say the sixth term of this series is equals to the sum of blah blah, third, fifth, and ninth term. It looks pretty random. So they like to give these kind of questions, okay, or this kind. So the trick to doing these kind of questions is to write down all the relations, every single relation that they state in the question. And often the algebra will look quite difficult, but it's important to persevere. Okay, so we have to write everything out very carefully. So let's have a look at this question over here. So consider all sequences of numbers with distinct terms, which follows a geometric progression. So geometric progression is the one with the common ratio, such that the first, second, and fourth terms of the sequence are three consecutive terms of an arithmetic progression. And let's add a word respectively. Okay, so let's say we want to find the common ratio of this geometric progression. So take a while, pause the video, and try to answer this question. Okay, so the question says that the first, second, and fourth terms of the GP are three consecutive terms of an AP. So we can let the starting term be A and the common ratio be R. Okay, and as for AP, we can let the first term be B and common difference be D. But do realize that this arithmetic progression, it doesn't have to be the first term of the arithmetic progression. It can be somewhere in the middle of an arithmetic progression as long as it's part of the arithmetic progression and they form three consecutive terms. Okay, so let's write it out like so. So the first term AR and the fourth term would be AR cubed because we are skipping the third term. And for the arithmetic progression, the first term will be B, second term B plus D, and fourth term. And the fourth term will be the third term in relation to these in the arithmetic progression, which is B plus 2D. So now what we realize is since we added the word respectively, right, we can actually compare these two. We can actually equate these two and change all the B's to A's. So now we want to compare all these. So A equals A isn't exactly very meaningful. So if we compare the second term and the fourth term, we have two different ways of expressing it. So the first one will be AR equals to A plus D, and the second one will be AR cubed equals to A plus 2D. So next, we want to express both of these equations in terms of D. So the first one will be AR minus A equals to D just by moving the A over to the left side. And for the second one, it's AR cubed minus A equals to 2D. Then we can sub in this value of D into our second equation here to get 2 times AR minus A. So if we equate this together and write it out, we get something like AR cubed minus A equals to 2 times AR minus A. And if we divide both sides by A, we get R cubed minus 1 equals to 2 times R minus 1. And if we expand this out, we'd get R cubed minus 2R plus 1 equals 0. And we can use our GC to solve equations because they are cubic and above, and we don't have a formula to solve cubic equations. So the results we should get is R equals to minus 1.62, R equals to 1, or R equals to 0.618. Okay, so at first glance, all these three answers look like they should work. But for this question, they want sequences with distinct terms. So it's very important to reject R equals to 1, because if not, our GP will just have the same term over and over again. So let's say 2, 2, 2, and then they won't be distinct anymore, right? But this is not always the case. So sometimes, if they don't have the word distinct, sometimes people forget to include this very obvious option, R equals to 1. So it just depends on the question. And take note, if they say distinct, then just remember to reject R equals to 1. So we've come to the end of today's video. Thank you so much for tuning in. And do stay tuned for our next video. We'll be talking about summations in series, the second part of this chapter. Thank you.